In the lead belt of southeastern Missouri, the largest lead mining operation in the United States has been carried on since 1720. The original operation was French. American interests have dominated the mines since the Louisiana Purchase in 1803. The lead belt lies in the foothills of the Ozark Mountains, within 65 miles of St. Louis. An outstanding feature of the lead belt, the huge chat piles left from the millions of tons of lead removed in past years. Chat is the crushed rock from which the lead has been extracted. Arriving at the mine, the men change to their working clothes in change houses, provided with individual lockers, showers, and washrooms. Loading of the mine cage at the shaft is regulated by safety measures. Only a specified number of men for each cage in the loading zone at a time. Each miner must be equipped with a safety hat, hard-toed footwear, and a lamp. 400 feet below the surface, the miners reach the main haulage level. Mine passenger cars, called cootie cars, transport them to their working areas. The 24-inch gauge track is electrically welded. Such welding is possible because the uniform year-round underground temperature of 60 degrees eliminates problems of expansion and contraction. The worked-out areas now serve for the location of the main hauling system and provide wide, ample clearances along the right-of-way with plenty of headroom for the overhead trolley wire. When underground mining was started, the shaft was sunk directly into the ore body. Now mining is carried on by the room and pillar method. As the work progresses, removal of the ore leaves large, open rooms. In order to better understand the operations, let's look at this animated drawing. First, the ore bodies are located by the diamond drill. From a nearby shaft, the miners cut a drift to reach the ore bodies. The path of the drift is carried on at a rate of 8 to 10 feet per day by successive rounds of drilling, blasting, and removal of the muck. Pneumatic drills bore approximately 28 blast holes, 9 feet deep to each round. Wet drilling and proper ventilation minimize rock dust. Water is forced through the machine and the hollow steel drill to the bottom of the drill hole. The holes are loaded with about 200 sticks of dynamite. Cap wires from all the holes are then connected in series and hooked up to a magneto-blasting machine which detonates the charge. After 4 hours, natural ventilation has cleared the mine of smoke. A mechanical loader or shovel removes the broken rock from the drift, depositing it in the mine car at the back of the loader. The mine car shown is coupled to the loader and moves back and forth with it. This prevents spilling of the rock. A trainload of waste cars is made up and hauled to the nearest waste rock shaft, where the rock is hoisted to the surface for disposal. The lead ore, called galena, a sulfide of lead, is found embedded in limestone and is seen as shining particles. The southeastern Missouri lead district is one of the few areas where no other metals are associated with the lead to any great extent. In hundreds of stopes scattered through the mines, miners are drilling holes into the ore in preparation for blasting. Wet drilling is employed in all types of mining throughout the lead belt. In this operation, the pneumatic drills are mounted on columns and connected with an air feed, which advances the drill against the rock. After the drill holes are loaded with dynamite, the explosives are detonated by lighting the fuses with a timed sparkler, which ensures proper time allowance for the lighting of all drill holes. The actual blast cannot be photographed. 4 hours after blasting, which allows for the clearance of smoke and gases, Drillers and foremen conduct a thorough inspection of roofs and walls to remove any loose or hanging materials. Broken ore is loaded into mine cars by electrically operated loading machines, capable of loading all of the ore broken during an 8-hour shift. This often amounts to 100 cars. A loading machine is almost human in its responsiveness to the delicate controls. This mechanism is of the self-contained Caterpillar tractor type and can be moved under its own power to new locations. Nobody knows exactly how much lead has been recovered from the lead belt mines in the last 200 years. Some, of course, was mined under the French beginning in 1720. Except for brief intervals, mining operations have been almost uninterrupted since that time. These high, cleaned-out stopes constitute the most impressive visible evidence of past operations. Following the horizontal body of ore, miners have drilled and cut and blasted for decades, yet nowhere will one see a single piece of timber support. The aftermath of all this work is found in great catacomb-like chambers, nearly 200 feet high in places. How much ore remains in the lead belt? No one knows. But the region is now, and for years to come, promises to be the foremost producer of lead in the United States. Miners become as skilled as trapeze artists, working on high platforms suspended from the roof scores of feet above the floor of the stope. Skilled miners swing back and forth on the walls of the stope, scaling down loose and hanging material to make certain that there's no loose rock or other threat to the safety of the men below. With constant improvement, ore is being mined today that would have been impractical in the past. Miners drilling high in the roof are protected from falling by the wearing of safety harnesses fastened to the platform. Safety is the paramount consideration at all times. As drilling progresses, the work is carefully inspected by the foreman. In these large stopes, prospecting and mining is continuously carried on. Large boulders are drilled and blasted to facilitate removal of the ore, while surveyors measure the stopes and gather data to keep mining maps up to date. Through vast underground cathedrals, ore trains go to the shafts where the ore will be hoisted to the surface. It's hard to realize that man has carved these gigantic stopes with their massive pillars. So similar are they to the fantastic forms carved by Mother Nature and the elements through the centuries. But it was the persistent toil and ingenuity of the miner, working in darkness by the flicker of a small miner's lamp, which created these royal gorges. Electric locomotives haul trains of 25 to 50 cars as much as 6 miles inside the mine and at speeds of 9 or 10 miles an hour. Prior to dumping, the entire ore train passes over automatic scales that weigh each car as it passes without uncoupling. This complete railroad terminal, located 400 feet underground with heavy trains arriving every few minutes and departing empty, may well be likened to that of a great city. At the bottom of the ore shafts are located the rotary dumps. The cars are dumped into the ore pockets 3 at a time without uncoupling. From the rotary dumps, the ore falls into the skip pocket and slides to the skip loading chutes, which are equipped with hydraulically operated gates. These enable the skip loading operator to control the flow of ore into the skips. An ore skip is loaded approximately every 30 seconds. That's a rate of 100 skips per hour. Skips are hoisted to the surface at a speed of 12 to 1,500 feet per minute. Ore is dumped into bins from which it's transported to primary crushers. Surrounded by huge chat piles, 5 large crushing, concentrating, and flotation mills are located at the ore hoisting shaft. To handle the 22,000 tons of crude ore that are brought to the surface every 24 hours. The run-of-mine ore flows to these large drum feeders, which maintain a constant feed to the primary crusher. Dry crushing is performed in 3 stages to prepare the ore for further treatment and recovery of its lead content. In the first stage, the primary gyratory crushers break the ore to fragments about 3 inches in maximum size. The ore then goes to the secondary crushers for further reduction in size. En route, it moves under a large electromagnet, which removes fragments of steel or iron. After passing through dry vibrating screens, the ore is transferred to the main storage bins at the head of the concentrating mills. At the top of the conveyor is a device which automatically takes samples at regular intervals. From the analysis of these samples and from the record of ore tonnage, it's possible to determine the amount of lead contained in the ore which comes to the mill each 24 hours. At the top of the mill, the dry crushed ore is conveyed to a spreading machine called a tripper, which travels over the tops of the ore bins and distributes the ore. The tripper diverts the ore stream from the conveyor belt into compartments, representing the main ore bins. Separation of the lead mineral from the ore begins with the elevation of the pulverized ore from the storage bins. Water is added, and the wet pulp discharged in gathering boxes, from which it flows to wet screens. Vibrating screens separate the pulp into oversized and undersized. The oversized, which flows over the screen, is sent to the rod mills to be further reduced. The undersized, passing through the screens, goes to the classifiers. The oversized is ground in rod mills, which turn at the rate of 18 revolutions a minute. It's fed to the mill with enough water to prevent overgrinding. Ore is pulverized by the tumbling of the rods as the mill revolves. In the hydraulic classifiers, the sands are separated into 30 different sizes. Of these, the finest are the slimes, which overflow here and are next sent to another part of the plant for treatment by the flotation process. The different sizes of classified sands are treated on concentrating tables to separate the lead from the waste. The various sizes are treated on different tables. Size ore from the classifier is introduced at the head end. Clear water flows constantly over the deck. The motion of the deck causes the galena, indicated by the dark area, to separate from the waste and discharge from the end of the table. Long, narrow strips of rubber called riffles divert the mineral particles. At the same time, the waste flows over the riffles and discharges from the sides, thereby separating the minerals from the waste and yielding 3 products. 1, a lead concentrate. 2, a low-grade product called middlings, which is returned to the grinding circuit. And 3, a product called tailings. Tailings and waste from the flotation machines are electrically pumped to the tailings ponds. The dewatering of the mineral product of the concentrating tables is done by a vacuum filter and dewatering drag. The wet pulp is fed to the filter. A vacuum pump draws the water through a porous filter blanket, leaving the lead concentrate adhering to the blanket. As the filter rotates, an automatic valve periodically releases the vacuum, dropping the dewatered lead concentrates into a hopper. The concentrates are then elevated to storage bins, later to be shipped to the smelter. Slime from the dewatering machines is pumped into a mixing tank where chemicals are added. The chemically treated slime is next pumped to flotation machines. The ore pulp enters the machine and is continuously agitated by air. The air agitation, together with a chemical collecting reagent, causes the formation of a froth, which rises to the top of the pulp and overflows. Due to the presence of a collecting reagent, the minute particles of lead mineral are induced to adhere to the bubbles. Thus, lead mineral rises out of the pulp and overflows. The lead-bearing froth from the air flotation machines is subjected to re-cleanings, in which the agitation is effected mechanically instead of by air. Flotation concentrates from these machines, assaying over 70% lead, are sent to the filtering and drying plant for dewatering. After thickening, the concentrates from the flotation machines are pumped to revolving drum vacuum filters. By application of vacuum, the lead concentrates are held to the face of the filter drums and thus dewatered. Then the vacuum is released and the mechanical scraper removes the filter cake. This filter cake contains about 13% moisture, which is too wet for shipment to the smelter, so it's further dried by passing through a gas-fired cylindrical dryer. The dried concentrates are dropped into a belt, which conveys them to a loading machine. A typical grain loading machine deposits the concentrates in boxcars. This mechanical loader enables uniform distribution of the concentrates in the car. At Herculaneum, Missouri, 35 miles from the mines and mills, is located the smelter, which has been in daily operation since 1893. Here, the high-grade concentrates from the mills receive their final processing. Every day, long trains of boxcars containing the concentrates arrive at the smelter. From each car, samples are taken for assay to establish its moisture content and the exact percentage of lead. The plant laboratory also maintains close control of smelting operations. Scoop grain unloaders are used to unload the ore into mixing bins, where fluxes will be added. All the fine materials around the plant go into the sintering mixture. Additional fluxes are limestone, silica sand, iron oxide, and granulated slag. The collected fluxes and concentrates are delivered by conveyor to a huge pan where they're thoroughly mixed. Pallets carry the mix under gas-fired burners. During this slow process, ignition takes place from above. Suction fans create the necessary draft in a downward direction through the pallets of sinter mix. The method of igniting the mix may be likened to a man lighting his pipe and drawing air through to keep the tobacco burning. The smoke and fumes pass downward through the pipe bowl. Similarly, the gas burners ignite the sulfur in the mix. The suction of the fans draws smoke and fumes down through the sinter bed. The fumes are collected and treated for the recovery of lead content. Burning for 10 to 15 minutes reduces the sulfur content and leaves the pellet in the form of a porous cake or clinker, which is cooled by a water spray. From the pellet, the steaming hot sinter cake passes over a grizzly and is dumped into a car for delivery to the crushing plant. Through the openings of the grizzly bars, the finer material passes to a hopper and thence to a conveyor, which carries it to storage bins where it's kept in readiness for the final roasting, after which it may be smelted. Underneath the blast furnace bins, an electrically operated Larry car collects the various fluxes required for the charge. The charge for smelting in the blast furnace consists of sinter, coke, and slag. When the charge has been collected, the Larry car runs over a pit and drops the charge into a blast furnace charge car below. After the transfer is completed, the charge car is elevated to the charging floor of the blast furnace building. The blast furnaces require periodic relining. They're 20 feet high, with a hearth 50 inches wide and approximately 16 feet long. The hopper of the charge car, electrically operated by remote control, is rotated and dumped into the top of a furnace. The blast furnaces are operated continuously in 3 8-hour shifts, 7 days a week. Furnaces are provided with inlets which admit the oxygen for burning the coke. Air is forced by large blowers through a bustle pipe to the inlet and then upward through the charge. Slag is tapped from the furnace intermittently. The heavy lead, metallic, and matte, a combination of other metals with sulfur, settle on the bottom of the hearth, while the lighter waste product or slag flows over the top and into the slag pot. At the side of the forehearth, the matte is tapped from the bottom and flows into a matte pot. And this is then transported to the granulator. Matte is a combination of copper, nickel, iron, and lead sulfide. In molten form, it's poured into a high-pressure water stream. The force of the water, the sudden change in temperature, solidifies the matte into small particles, which are sold for their metal values. Each furnace produces 200 tons of crude lead every 24 hours. This, after processing in the refinery, yields 150 tons of refined lead suitable for market. From a furnace, the lead is taken to a drossing wheel, where part of the dross is removed. Dross, containing such impurities as copper and nickel, along with a high percentage of lead, is skimmed off with a large ladle. It's poured into molds to form rough pigs, which will again be run through the blast furnace to recover their lead content. After this preliminary skimming of the dross, the lead is taken to the refinery for the further elimination of its impurities. The lead pot is hoisted by an electrically controlled crane, which is operated from the floor, and the metal is poured into the rough drossing kettle. A perforated dross basket with a capacity of 3.5 tons is immersed in the kettle. Skimming off the dross, the basket is hoisted by the crane and suspended above the kettle while the metallic lead drains back. A centrifugal pump is inserted under the small remaining quantity of the dross and serves to pump the metallic lead to an adjoining kettle. Different types of lead are made according to the uses for which the metal is intended. Here, the remaining dross is removed, and the lead's allowed to cool to 625 degrees Fahrenheit. This is called chemical lead. Other types of lead are made where it's necessary to remove the silver to improve the purity of the lead. Zinc is added to the metallic lead in the refining process for the removal of silver. The zinc alloys with the silver, then floats to the top and is skimmed off. This beautiful seal of the great state of Missouri is made entirely of silver recovered from refining Missouri lead. Designed by the distinguished American sculptor Paul Manship, it has been donated to the battleship Missouri. The zinc also removes whatever copper and nickel are left in the lead. After removal of the silver, the lead is pumped into a gas-fired furnace for removal of the 0.6% of zinc which has been left in the course of the desilvering process. Pure lead from the dezinking furnace is pumped into a holding kettle for partial cooling. Thence it's piped to the casting wheel, where it's poured into 100-pound pigs. The metal flows through a pipe supported by a harness over the operator's shoulders. This operation calls for the skill of a three-armed man, as the workman pours and simultaneously skims the metal with paddles in both hands. Rotation of the casting wheel is electrically controlled by the operator. The filled molds pass through a continuous spray of cold water applied at top and bottom to cool the lead. An automatic marking device stamps the identification or production number on each pig. 5 at a time, the 100-pound pigs are plucked from the casting wheel by an ingenious device called a pick, which operates by compressed air. With each load, the pick is swung around, and the pigs are stacked in piles 7 high. The lead pigs are cast with protruding ears to facilitate handling and shipment. An electrically operated lead loading buggy picks up the 3,500-pound stack of pigs, lifting them by the ears, and transports them to the weighing scales. After which, the metal is transported by electrically operated loaders and delivered to freight cars on the refinery siding. With each car loaded to its capacity of about 50 tons, the metal lead is sent out to the many various industries to be converted into useful articles for mankind. This pig of lead, weighing 100 pounds, has been obtained from the smelting of about 138 pounds of concentrate, which by milling have been produced from approximately 3,300 pounds of ore taken from the mines. In the milling process, about 3,100 pounds of almost lead-free limestone was discarded as waste, locally called chat. The industry consuming the largest tonnage of American lead is the automotive industry. Almost every car uses lead in storage batteries, solder and bearing metals, and even in brake linings. In addition, lead is used in gasoline for better performance. Lead storage batteries are also widely used in airplanes, submarines, industrial lift trucks, power plants, farm and car lighting, and mine locomotives. And humble lead also plays its part in preserving and protecting old and new buildings in the form of white lead for wooden structures and red lead for steel. Lead plays a vital part in electric power transmission and in telephone communication as a protective sheathing for electrical conductors. Lead's also extensively found in plumbing systems and in the chemical industry wherever sulfuric acid is made or used. Lead has many other uses, far too numerous to detail here, such as ammunition, type metal, foil, collapsible tubes, insecticides, and sinkers. Such is the story of an American mining community. Monuments to the tireless industry of many decades, the great chat piles, whose volume is considerably larger than the pyramids, loom against the sunset, a record of achievement and a hint of the wealth still buried in the lead belt of southeastern Missouri.